Okay, good morning, class. Today we are going to have a look on this flexibility method, which we can apply to beam and frame. Okay, so I hope you have participated well in my class last week, because we have learned flexibility method that apply on truss. The procedure of these flexibility methods are the same. Only we will have a little bit treatment, okay, on the compatibility equations, which is dealing with this delta. If you still remember, the delta is the displacement. Okay, for truss, in the virtual work method, we use this equation, summation NNL over AE, okay, for truss. And now when we are looking at this beam or frame, we're dealing with more on this bending moments. Okay, so the displacements that we will be used later will be integration. Okay, M over EI. So we are going to use the integration later for beams and frames. But if the beams and frames, you need to consider the axial effect. So we also need to plus this effect dealing with this axial. Okay, I will call this displacement is dealing with the axial effect, and this is dealing with these moments, okay, or bending, okay, effect. Okay, so you need to be you need to understand the structure well. Okay, either this structure is subjected to dealing with bending or governed by axial type. Okay, so then you will be able to determine the real displacement that due to the real behavior. Okay, so let's start our lesson today. So this is our lesson outcomes. Okay. So there's a good music. Okay. So check the. Thank you. Okay. All right. So we will have to address these lesson outcomes. Okay. There are 3 lesson outcomes. We would like to achieve this week. So first of all, we are going to identify the redundance for the beams and frame, and again the indeterminate beams and frame. Okay. Then we are able to formulate the compatibility equations. Okay, to solve these redundant forces which deal with the bending type. Then we should be able to determine the support reactions, okay, moments, and also the displacements that subjected to external load support settlements. So in this case, we don't commonly deal with temperature effect or the fabrication error. Okay, so but support settlements still governed here. Okay, we will have a look on the example, okay, by this week. So this is to get a revision back, the degree of static indeterminacy for beams and frames. We are going to use these equations. Okay, so R will be the support reaction, N is always 3 for 2D, but 3D there will be 6, and the C will be the internal hinge. Okay, so these are the general procedure. Just to refresh back, okay, what we need to do for these flexibility methods. Okay, so first of all, we need to identify how many redundants. Okay, the number of redundants. So we will have a value here, let's say 1. Okay, so means that you are going to remove 1 redundant here. Okay, you need to identify either this redundant externally or internally chosen. Okay, so you need to construct primary structure and virtual structure. So now you will always construct 1 only. Okay, 1 number of determinate primary structure. In this case, we name it M naught. Okay, so then you need to remove the n unknown. This n must be your D value. Okay, if you have one redundance, means that you need to remove one. Okay, these are redundant force, but the real loads, okay, in as in your real structure. Then you construct a virtual structure, which I name it here now M1. Okay, so how many number of redundant structure also depend on your D. So if your D is equal to 1, okay, you construct one numbers, okay, of this one redundant structure. So how to create this redundant structure? You can take this primary structure, okay, the geometry, okay, the geometry will be the same, okay, the support will be the same, okay, but you remove all the real loads. Okay, then you apply back the redundant force 1 kilonewton, 1 unit. It might not be always 1 kilonewton. It depends on your redundant force. Okay, if you have take out the redundant force in terms of vertical or if it is vertical or horizontal force, then you apply 1 unit force that is same with your real structure. So let's say 1 kilonewton. But if you take out in terms of moment, okay, then you apply back in moments, 1 kilonewton meter. So this must be very clear at the position of this redundant force, and the direction will be up to your assumption. Okay, so and then you analyze both of these determinate beams and frames. Okay, you need to know that in this process you are actually changing the indeterminate structure to feel imaginary, not real. Okay, but they are determinate structure that you can solve by using the equilibrium equations. So let's try on this. Okay, so we need to determine the degree of indeterminacy of these cases. So can I have your participation? Let's try on number 1. I suppose number 1 and number 2, okay, number 1 and number 2, they are actually have the same results, only the position of the roller is different. Okay, can I know the D is, how to calculate this D for this case? Can you help me? How many?
3.
Yeah, reaction is 4.
3. 4.
4. Yeah, there are 3 at the base. Okay, 1 at the roller.
Oh, the moment includes also another.
Of course, because this is a fixed support we have. Maybe I just make sure everyone know. Let's say this is A. Okay, there will be AY, AX, and MA. Okay, this, let's say this is at B, so this is BY. So how many N in this case?
3.
3, yes. There is no internal hinge, therefore it is 1 degree.
Yes.
So you can remove any of these support reactions. BY, okay, MA, okay, even not AY, okay, but just make, yeah, BY and MA, okay. So just make sure this system is still stable, okay, and because sometimes when the when the structure is stable, you still can use this equilibrium equation to solve. But normally you cannot use the summation, the equilibrium to solve these unstable structures. Okay, so this case 2 is the same, D equal to 1. Okay, only this roller at different place. Okay, so how about case number 3? Can I have
4 minus 3.
4 minus 3 still equal to 1. Okay,
Yes.
so you can remove. Can you suggest which support reaction to be removed?
AX.
Okay. Yeah, you can remove either BY, okay, but you shall not remove AX. Remember that if you remove the AX, this A become roller, right? When there are three parallel support reaction, these systems are going to unstable. It's going to move. So we don't do that. Okay. So how about case number 4? This case number 4.
6 minus 3.
Yeah, thank you very much. So this is 3 degree. So this is how to remove this redundance. Way to remove. Okay, let me name this AY, AX, MA. AY, BY, BX, NP. So how many redundants to be removed here in this case?
3 redundant.
Yeah, so you need to remove 3 of these support reactions. So which one is you can remove?
I think at the BY middle.
Okay, you can remove all the support reaction at B. Okay, BY, BX, MA, you just remove. Therefore, you are going to have 3 redundant forces which you apply back later. The first one may be BY, the second one BX, the third one MA. Okay, imagine because I do not draw it now. Okay, then these determinate systems in this, it will be looks like this. Okay, a cantilever beam. Okay, when you have removed all the BY, BX, MA. Okay, you may also change this to another types of system, a simply supported. There is no problem. How to change it to this simply supported beam? Which one to remove? May you help?
MA,
Yes, MA missing.
BX,
Yeah,
and MA.
yeah, BX and M. Sorry, this
Madam,
is MB. Okay, so yeah,
madam,
yes.
the redundant to be removed should be from the support reaction only.
For this beam and frame, it will be more easier for you to get from this external. Okay, but for the truss, we can remove more easily, commonly the external and internal, where we remove the truss member force. Okay, but you can do so in the beam as well. Okay, if you have any member force that you want to remove. Okay, but commonly we will, if the support reactions allow us and it is still stable, we will just remove externally first. Okay, so let's try case 5. That is a good question. Okay, so let's calculate this D.
5 minus 3.
Yeah, thank you. 5 minus 3, there will be 2. So you need to remove 2. Okay, so in this case, you may remove just a roller. Okay, both of this roller. So it become a cantilever beam again. Okay, or you want to change it to this simply supported beam, there is no problem. Okay, so as long as you just kick out the 2 redundants. How about case number 6?
9.
Okay, so for this case number 6, they actually I will suggest you to because this is a double system. Okay, which this let's say I put in this beam 1, beam 2. Okay, actually beam 2 is supporting beam 1 at this roller, at this connection. Okay, so I would suggest you to analyze these beams separately. Okay, how to do that? You draw your beam 1 and you draw your beam 2. So how to draw your beam 1? Okay, so your beam 1 you'll be just remained in such. I hope you can see this. Okay, so let's say A, B, C. So this is A, B, C. So if you can see that this case beam 1 case 6 beam 1 is actually same with case 5, right? So this D is equal to 2. Okay, you can analyze beam 1. Okay, first, no problem. Once you get your support reaction, By, okay, so this By is going to be act as a loading to your beam 2 because beam 2 is carrying your beam 1. Okay, of course you are carrying, like, let's say you are carrying a box. So the box weight, okay, will be transferred to your hand, let's say. Okay, so meaning that this beam 2 is supporting beam 1 at B. So the By later will become a point load to beam 2. So when you are analyzing beam 2 later, you will find that beam 2 is actually, sorry, I'm drawing just two. This is B. Okay, this is A. This is determinate D equal to 0 for beam 2. Okay, for beam 1, D is equal to 2. Okay, you just analyze beam 1 first using this force method or other methods, and then you solve for By, and then the By will become the loadings to your beam 2. Okay, do you understand my explanation? So
Yes.
yeah, so in this system, the D is equal to 2. Means that once you remove 2 redundant at beam 1, okay, so then you can solve all the system. Okay, so this is a trial for you. You can yeah, experience yourself later with more examples. Okay, so now this is yeah, actually another, yeah, on how to construct the primary structure and the redundant structure. Okay, so using this one of the case just now. So once you have identified how many redundants to be removed, okay, from your case, this is real case. Okay, so then you need to construct primary and redundant structure. Your primary structure M0, you need to remove 1 because your D is equal to 1. So you remove 1 redundant force. You decide which one to be removed. Okay, just make sure it is a stable structure. So for a more easy case to analyze, okay, then you can just analyze as a cantilever beam. Okay, so where you remove your VB or By. So now your By has been removed, means that roller, if you can see that roller is missing, okay, because you are removing By. Okay, no more roller, and the load is still there. Okay, then you can analyze this primary M0. Okay, for M1, you need to apply back this 1 kilonewton. Okay, at the By. Okay, because By is the redundant, so you apply back By. Okay, and then the real load is missing. Okay, real load you take out. So this is how yeah, you draw your primary and redundant structure. Take out. Okay, so then the step 2 is about the compatibility equations. Last week we have tried to write the compatibility equation. There is nothing different, okay, for the beams and truss. The only treatment is the displacement, because for truss we are using axial force, but for beams and frames we are more concerned on the moment. Okay, therefore the equation to get this displacement for deflection for beams and frames is using this integration. Okay, so I will not go very detailed explanation, okay, on this, okay, because we have gone through earlier. Last week I haven't talked about this. Okay, so maybe we will have a look on this case. Okay, so this is a real case. Okay, real structure, and you have determined that the to 1 degree. So you need to remove one of the redundant. So here choose MA Okay, choose MA as redundant. Okay, as R1, let's say. So for this M node, okay, if you can see that this fixed support has changed to the pin support. Okay, means that the roller has been taken out. Okay, but for those who are not sure if the moment has been taken out, what happened? The fix, is it become roller or is it become pin? You keep confusing about that, so you don't draw these uh, supports. You just draw in terms of forces, support reactions. Like for example here, instead of drawing the support, you just draw AY and AX. Okay, then you will understand that MA has been removed because you have choose MA as your redundant. Okay, so BY we do not remove it, so it's still here BY. Okay, so then this is your M node. You can just analyze just like a simply supported beam. Okay, with a pin and roller at the ends. Okay, then okay, for M1 structure, you need to apply back because you are choosing moments to be removed, right? So now you need to apply back 1 kilonewton meter, okay, for your R1. So where is your R1 is MA, right? So now your MA, you put a 1 kilonewton meter here. Okay, either clockwise, either counterclockwise, you make your assumption. Okay, your result later, your answer will tell you if your MA that R1 that you have solved is negative, meaning that your assumption, your direction is wrong. Okay, you need to, it is supposed to be the opposite side. Okay, so similarly, you are still applying these equations. Okay, only now we don't use this delta. Okay, instead we use this theta. But there is no problem. You can keep using this equation, but you need to know that now you are solving for some rotation instead of uh, this deflection translation displacement. Okay, so now yeah, this is when you have this d equal to 2. Okay, we have also tried to write d equal to 3 in our last lesson. Okay, so please get familiarized with this. For those who haven't since my last lesson haven't write this, okay, please write it today. Okay, okay, so we are going to try on the two example, 1A and 1 example 1 and 2, okay, today. Okay, to make sure you have more understanding on this how to apply these flexibility methods. Okay, you need to open to my another notes, okay, on the PDF file. I haven't opened it. Okay, which is 7 pages. Okay, you can download from the UFuture. Okay, but now I have put it in the PPT file so that I can write something more easily here. Okay, but actually I'm referring to that handout. Okay, can you see my slides now?
Yes.
Okay, it's on Beams, right?
Yes.
Yeah, thank you. Okay, now let's try on this example. I have put it 1A and 1B. Okay, because they have some connection. Okay, so now this is the case that we have determined the D just now, right? D is equal to 1, and then it didn't ask you which redundants to be removed now. It asks you to decide. Okay, so let's have a look on this question. Determine the reaction at roller support B of the beam. So it asks you to determine BY. So these questions already ask you to determine BY. Therefore, you directly choose BY as your redundant. Because one you solve for your R1, you solve for your question 1A. Okay, So this also make you to decide. If you decide to choose, let's say MA, okay, as your redundant, there is no problem. After you have obtained your MA, then you need to from the equilibrium equation for the real structure, that you put it back MA, what is your result, then you solve for your BY. Okay, so let's have a look on the process. Okay, so we need to construct the M0 and M1. Just now when we take out the BY, okay, BY you take out, so there will be no BY here, if you can see that, no BY. Okay, so it become a cantilever beam. Okay, that's done for your primary structure. Remain the loads, don't take out. Okay, so then you can copy everything here from your primary structure, your geometry, your support reaction to your redundant structure, M1. So what is the treatment? Remove the loads. Okay, we remove the loads, real loads, and then we apply back By or R1 equal to 1 kilonewton. Okay, which you have already put it here. Are you okay, class? Can you draw your the M0 and M1 for this case?
Yes.
Okay, if you need me to explain again, you just need to let me know. Okay, so if you're okay to create this M0 and M1, so the next thing is, because we want to get the compatibility equation done, and all this displacement requires moments. So you need to take the bending, determine the bending equation or bending function. Okay, so we need to cut sections for this primary system and redundant system. Okay, so let me cut this. Okay, so there is rules to be applied here. Okay, make sure you cut the same section or with same range for both structure, M0 and M1. Okay, so meaning that if you cut 2, okay, for M0 you cut 2 for M1, and they must have cut at the same range. Okay, means that from A to C for M0, A to C for M1. Okay, C to B for both this M0 and M1. The second will be start your X, distance, I will call distance X, the same point. Means that if you start your cut section from, measure your X from B for M0, do the same thing for your M1. Okay, the third one, okay, use the same sign of the moment, let's say X. Okay, so if you are talking about this cutting section, normally we in your chapter 1 we will use the positive sign. Okay, so you just use the positive sign for both of these. Okay, if you want to use negative sign for this case, no problem, you still get the answer, but make sure your primary M0 and M1 have the same sign. Okay, same sign means that if this is clockwise, for this CB you also apply clockwise. Okay, so there are 3 rules here, please take note. Okay, so now I'm going to analyze the M0 and M1. Okay, here. Okay, so I'm going to cut because there is a 50 kilonewton here, I have to cut 2 sections. Okay, because there are 2 different bending I will call function in this case. Okay, so now at this CB, okay, I don't have, I'm looking at this section. Okay, this section, I'm drawing this section. Okay, or the right section. Okay, so therefore the left section is not under my consideration. Okay, so I don't have any lots here, so therefore my moment is 0. Are you okay? Am I too fast?
Yes.
Okay, so I will quickly do for M1 right now as well. Okay, so the same section. Okay, I cut and I start my X from B, and I'm considering the right section, so which means is this one. Okay, the left section is not under my consideration. So now I only have 1 kilonewton, okay, in my section. Okay, so there'll be 1. So 1 multiply X, 1 multiply X. Okay, so because this is opposite, so I have a positive sign. Okay, so I just put a positive here just to make sure you know that I already take note on my sign. Okay, so it is actually X. Okay, my moments here for CB. Okay, now I'm considering another sections AC or CA. Okay, and again I'm considering the right section. I draw another. Okay, this is my in a rectangle. Okay, this is my section that I considered, and I have this 50 kilonewton. Okay, at my section, so I need to know what is the distance to this section, to this cut section. Okay, so I know that CB is 6 meter. Okay, so what is my distance here? This X always means to go up to the cut section. So meaning that this X distance is up to here. This is X. The whole B to the cut section is X. Okay, maybe I put it here, X. So what is the distance C to the cut section? Class?
X minus 6.
Okay, thank you. X minus 6, because this is 6 meter. Okay, so you need to calculate this quickly. So now my moments here will be the loads 50, and distance is X minus 6. Okay, and it is acting the same direction, so I have my negative sign for this moment. Okay, so now I'm going back to this M1. Okay, but there is no other loading in between. Okay, these two cut section, they must have the same value. Okay, so it should be X. Okay, if you don't believe that, then we can again 1 multiply. Now the X is up to this cut section. Okay, so 1 multiply X, and then it is acting oppositely, so it is positive. So you get an X here. Okay, so now you have solved for this all the moments. Okay, you can put in the table or directly put in the compatibility equations. So let us see. So shall I keep? So keep first. Actually, simple. Okay, so this is what we have calculated just now. We need to put in a table. Let's say you want to put in a table. This is M0. Okay, for member BC, you need to put a range. Okay, sometimes you put a range here. Okay, correctly. So this is from 0 to 6 meter. Okay, and this is from 6 to 12 meter. Why this is from 6 to 12 meter? Because your x start measure from B, meaning that x equal to 0 at B. So when come to C, the x already equal to 6 meter. Okay, so this is why you have but if you start your x from C for this section CA, the range will be from 0 to 6. Okay, so now you just need to transfer all these moments that you have obtained, okay, into this table. Okay, but if you have so, this is just a few few section, and it is not that confusing, you can directly put in your compatibility equation, okay, which is like this. So you still need to write your compatibility equations, okay, and now you need to this is not delta 1 knot, sorry, this we have earlier is delta 1 knot. Okay, so can you help me to change so that you will be not confused. Okay, delta 1 knot will be dealing with m what? M naught over EI, and from the range. Okay, let's have a look. We have this zero, so we don't have any consideration for member BC. We have to look at CA only. So this is for CA. The range is from 6 to 12. Following this, 6 to 12. Okay, and then you have the X. This is from your M1. Okay, this is from your M0. Okay, whether you want to write M0 first or M1 first, it's up to you. Okay, there is no different. Your EI can be put outside from the integration. Okay, then you can solve for your this integration. Okay, then go for delta 1, 1 is dealing with M1 multiply M1, which is also M1 squared. Okay, so meaning that you need to you might get confused with this. Okay, for those who get confused with this, so you write for BC first. BC is from 0 to 6, and then x squared dx plus, okay, for CA is from 6 to 12, and x squared dx. Okay, so this is BC, this is CA. So it actually equal to this as well. Okay, then you get your delta 1, 1 done. So once your delta 1, 1, oops, I can see, you can put it in your equations. Okay, remember there is no support settlement, so therefore it will be equal to 0, the delta 1. Okay, then you, in this equation 1, you have only one unknown, which is R1, and you solve for R1, and you need to know that R1 is the redundant that you have removed, which is BY, and you solve for BY cases. So you solve for example 1A. So this BY, you can put it in your 15.6, right? So you can put in your real case 15.6. Then you have AY. If you want to find the rest of the support reaction, what you need to do, you take a summation MA equal to 0. Oops. Okay, you take a summation MA equal to 0. Now, from this system, since you already solved for BY, you can get your MA. Okay, you can solve for your MA. Okay, and then you take summation FY equal to 0. You solve for your AY. And you take summation Fx equal to 0. You solve for your AX. Okay, so this is how you solve for other support reactions. If you want to solve for the bending, or draw bending moment diagram, so you use these the real values to cut section again, and then you can determine, okay, your any shear force, bending moments, okay, at any point, okay, of this indeterminate system. So now I want to have share with you, what if, okay, the support B has settled 50 mm. Okay, this is dealing with this delta 1. So be careful, this delta 1 must be referred to the point of interest, because this R1 you have removed is B, right? So therefore, this delta 1 is referring to the position of B. Okay, then now the delta 1 has value, okay, of this 50 mm. So what is the treatment? Let us just have a look on the compatibility equation. Okay. You no need to solve for the bending equation, redo everything again. The only treatment is applied at this compatibility equation. Okay, which this delta in the example A just now is 0. Now this is deal with support settlement or support displacement here. Why this is negative 0.05? Okay, there is some rules. There is a rules. Okay, if you refer back to my earlier last week, the notes last week, you read a rule that if you have a positive the direction opposite with by, you have a negative value. So let's see what is our by direction in. This is not that clear. It should be in virtual structure. Okay, let's have a look on our virtual structure. Where is our this one? Okay, the by is upward, right? So let's have a look on the rule. If it is opposite direction, okay, then you will have a negative value for this delta 1. So what is this direction for the support settlement? When support settlement, this supports, a roller, this supports is actually moving downward. Okay, but just now we apply by in the virtual structure is upward. So this is opposite direction. So you will have to apply a negative for your this support settlements delta 1. Okay, so now you need to resolve again this R1. Okay, this equation 1. Then now you can see that the by is 11. Just now is 15 kilonewton. Due to this support settlement, it become 11. Okay. So any question, class? Okay, so yes, for this example too, I'm not going to go very detailed. I will highlight which you need to take note. Okay, so now this example too, the question is to determine the support reactions. Okay, means that all the support reaction you need to determine, and it's not given to you which to be removed. So now if you look at the D is equal to 1. Okay, yeah, in this case, we choose AY as a redundant. Okay, so AY is a redundant, meaning that you take out the roller. AY is not, the one remain is BY, CY, and CX. Okay, so you can have a look on this. Okay, but I'm going to show you why we need to cut 3 sections. Okay, so you need to observe at both of this system. Let's observe at M0 first. Okay, whenever go the member, you cut a section, right? And any differential in terms of loading. Okay, so let's say A to B. Okay, is one of the section. Okay, cantilever ends. So you need to cut 1 section. Okay, so this is why you cut it here. And then from B to C, there is another member. Okay, yeah, a member. Okay, but it has been differentiated with this loading 2.5 kilonewton. Therefore, you need to cut 2 sections within this member. Okay, so now a total sections that you need to cut is 3 only. But if you look at M1, you actually in the common practice, you only need to cut 2. But still, please prepare the same section like what you have for M0. Okay, let's say maybe your M1 have more section, 4 sections to be cut. So in M0, you need to add another one so that both of these sections, the range, okay, are the same. And they start the X from the same place. And the same sign for the internal moments. Okay, they are the 3 rules that I explained just now. So this is why the 3 sections has been chosen for M0 and M1. Okay, then you need to look at which sections is more convenient to you. Either you start your X from A, considering the left side or considering the right side. So yeah, so this is how you choose how to cut a section and what is your range. Okay, so once you have solved for this, okay, do you need me to explain maybe how to get the M0 for this case?
Yes.
Okay, so I will explain on how to get this M0. Okay, let's say I have this cut section 1-1. Okay, my consideration of is during the left side. Okay, I put a circle here. Oh, sorry, the square. Okay, I'm considering the left side. The right side will not be under my consideration. So the loading on my left side is a UDL. I can represent this UDL as a resultant point loads here, which is the rectangular of this lots. So the distance to the cut section is X. Okay, so therefore you have the rectangle is 2 multiply X. Okay, and the distance to the cut section is half of the X. Okay, if you not clear, I'm talking what is the X. This is the X. Okay, I'm talking about this X. Okay, so now my moments for this cut section 1-1 will be 2X squared over 2. Okay, and it is acting the same direction, therefore it's a negative. So you get a negative X squared here. Okay. Okay, so next, I would like to considering the cut section 2-2 also for the left section. I extend now. I hope it's not that messy for you. Maybe I clear first. Okay. Okay. Now I'm determining this bending function for cut section 2-2, and I'm looking at these left sections. Okay, so now my X is from A to here, cut section 2-2. So this will be my X. Okay, so now I have two forces, two loading or two forces that will be acting to my cut section, which is one is UDL and another one is my BY. Of course, you need to determine your support reaction first. Okay, so now I will have I will choose to represent it in the point load for my UDL. Okay, but I don't know my 3.6 meter. Okay, so AB is 3.6 meter. Okay, sufficient. So now this will be 2 times 3.6. Okay, will be my loading. Just take the area of this rectangle. Okay, and then the distance to the cut section will be X X minus because I know that this is 3.6 divided by 2, and the total length is X, so it will be X minus 3.6 divided by 2. 3.6 divided by 2 is 1.8. Okay, I will just directly put x minus 1.8. Okay, so now I get the value. I also need this, the by distance. Okay, before I take my this, it'll be x minus 0.6. Okay, so I can get my moments right now. My moment, this one will be equal to, dealing with the UDL first, it'll be 2, 3.6, and the distance is x minus 1.8. Okay, and it is acting the same direction, so I have a negative sign. Okay, and then the other one is 12.77 is the by, and the distance is x minus 3.6. Okay, and this is acting oppositely, so I have a positive. So opposite, positive, same side, negative. So this is my moment. Okay, then I will need to simplify it every. Okay, the next one will be cut section number 3. Okay, then I'm considering the short section because it will get more easier. So I'm considering the right section right now, and my x start from C. So this is my distance x. So the moment is only dealing with this cy. So it will be negative 3.07 is my loads, and my distance is x. So, and it is acting oppositely. So I have a positive sign for this moment. So this will be negative 3.7x. Okay, do you have any question for me? Okay, so the range must be written correctly, where for these moments, negative x squared is actually applied to member AB with this range only 0 to 3.6. Okay, and BD will be from 3.6 to 5.1. This 0 is A actually. This 3.6 is at B. This 3.6 is at B, and this 5.1 is at D. Okay, and this is from C, and 1.5 is from D. So you need to be careful when measuring your x. Okay, if this is wrong, your compatibility equation will be wrong. Okay, so let's have a look on M1, but I'm not going to do this for you. You can have a look. Okay, so again, we are going to cut this. Make sure the section must be the same. Okay, and the moments just take from this M1. Okay, once you have get this M0 and M1 done, okay, so you can put it in this equation. Okay, let's see what is any special things here. Okay, remember one node is dealing with one and not. Okay, so you take both of these data, okay, from M0 and M1. So we start at AB first, 0, 3.6. And this is because a multiplication of negative x squared and the x. Okay, so how to get this is negative x squared multiply x. Okay, there is no nothing strange here. This is for AB, and this is for BD. Okay, this is M0, this is M1, and this is the range 3.6 to 5.1, and this is for DC. Okay, from 0 to 1.5. This is M0, this is M1. Okay, then you can solve for this delta 1 node. Okay, so then the delta 1, let's have a look. Delta 1 will be talking about M1 multiply M1 only. So therefore, this data is not used. Okay, in this delta 1. Okay, so this is for AB. Okay, where you have an x squared here, 0 to 3.6. And this is from M, this is from BD. Okay, and this is from DC. Okay. So for your R1, place all the delta 1 node, okay, that you have obtained, delta 1 that you have obtained. Then here you solve for R1. Again and again, I need to remind you that R1 is actually the redundant that you have removed earlier. Okay, which you have earlier removing AY. Okay. So AY is 2.93. Okay, so I'm not going to continue with this example 3. It will be our next class. Okay, so but I have something for you to do this morning. Okay, so make sure you have take your attendance. I will going to check the attendance. Okay, then I will show you what you need to do for the tutorial class in another hour. Okay. Okay, just Mina, you here with us? Yeah, you are here. Just Mina. Yeah, can you take your attendance? Salsa. Salsa is here. Salsa?
Yes, sir.
Yeah, can you help to take
Yes,
the
I
attendance? Okay.
Okay.
Mhm. Where am I now? 5A done? Have I checked 5A just now? I forgot. 5A done, is it? Oh, forgot about this. Yeah, done. I thought there is one cannot come today. Okay, so for today tutorial, I have put in the I discuss week 6. Okay, so now we are at week 6, and there are two sessions which we will be doing it in the class, tutorial 6A and tutorial 6B. Okay, so in this they are sharing the same handout tutorial question. Okay, I will open this tutorial question and tell you what you need to do for this class. Okay, so this is a tutorial question. Later, please take from the I discuss. Okay, there are 4 questions, A, B, C, D. Okay, so you can see that the redundancy identified for you. Okay, but please also recalculate the D, whether this is really D equal to 2 or 3. Okay, and then I want to go back to, so for this class, I want you to draw the primary and redundant structures, okay, for question for A to D. So we are not solving the redundant forces today, okay? We are just to draw the primary and the redundant structure for this problem. And then I think I shall add some more. Please determine where is the cut section as well. Okay, determine where is the cut section and where you start your X and what is the sign of your this bending moment. Are you clear, class? Class, I'm giving you a tutorial right now. Can you hear me?
Yes, madam.
Okay. Yeah. So I'm asking you to go to download the tutorial question from iDiscuss, and then there are 4 questions for A to D. You do not need to solve these redundant forces yet today, because we want to understand, expose you on how to draw the primary and redundant structures. Okay, so of course, in that questions, they already give you the redundants. But you are not, if you are not happy with this redundant, you can propose your own redundants. Okay, so today I'm going to monitor your WhatsApp group. Okay, so for those who have already draw the, let's say, solve for A. Okay, please quickly snap your question, your answer to the WhatsApp, and I will give feedback there. Okay, so I hope to give feedback for 4 questions before the class ends. Do you get what I mean? And you write your names. I mean, who post the solution to the group later. Are you clear, class?
Yes, madam.
Okay, I hope you, yeah, for those who not clear, please stay. You can ask me question later. Okay, and then in the I discuss, for those who have already answered the tutorial, please write that you have completed tutorial 6A. Okay, so now I will stop the recording. Okay, and then if you don't have any question, I see you next class, and then I will be waiting your answer in this chat room. Okay, for those who have question, yeah, you may remain. Okay, I'm still here. Okay, thank you, class.
Thank you, Doctor.
You have any question for me? The one who left here?
Madam,
Yes.
regarding the assignment that need to be submitted the last time,
Yes.
my group left only one passer only that we didn't submit due to
Are you the one who text me?
Yes.
Okay. I remember. I have yet to reply you. Because I'm having this class so early to this. Later, I'm going to reply your message later. Okay.
Because the moment I want to click submit, madam, my internet gone away. Yeah. I got stressed,
Okay.
madam.
All right. So
Okay.
yeah, I will reply you later. Huh?
Okay, madam. Thank you.
Yeah. I'm still with 9 attendees here. Any questions from you?
Wait, madam, I'm trying to find the question you asked us to do.
Okay, you go to I discuss. I don't want to give you here because I want you to visit the I discuss. Huh? Dayang, you have any question for me?
No, madam.
All right. Elvira? Fatin?
Okay, madam, I go first, madam.
Yeah.
Okay,
I'm
bye,
waiting.
madam.
Yeah, you
No,
quickly draw and then post it in the WhatsApp so that I can give feedback to you.
Okay.
Okay.
Thank you,
Have a nice
madam.
day.
Okay.
Nabil tu Nabil. Okay, madam. Bye.
Bye.
Okay, madam. Sorry, madam.
Okay. Nabil? Nabil?